Yeah,
right now.
audio connection's always much better through GoToMeeting than it is even by the telephone. So, okay, I got your email here.
Okay.
I'm not sure I have it in the right order. Is this the first set of problems?
I think probably the bottom one is.
Okay, let's open that one. This looks like it's in the 30s.
That is the one.
Okay.
I had a homework assignment, and I had to do number 31, 33, and 35, and I had no idea how to do them.
All right, let's take a look at them here. Let me reduce it a little bit and get my screen set up. Let me do it this way. All right, so this is proving trig identities, basically.
Yes.
Let me have a look at this for a moment. Well, we can do a couple things here. We could move the second item to the right side and improve that trig identity.
Oh, yeah.
And let's see, what would that look like? That would look like cosine x minus cosine y all over sine x plus sine y is equal to, now if I make this negative, it's the same as reversing the top.
Yes.
Okay. I'm thinking for a moment. I'm not used to proving trig identities in two variables.
Yeah, it is kind of weird.
Yeah, I mean, it's so hard for me not to cross multiply.
Yeah.
And I'd end up with cosine squared minus cosine squared equals sine squared minus sine squared. And then by moving things around, I would get 1 equals 1. Can you see that?
Which would be good.
It might, yeah, it might actually be instructive, even though this is something you're not allowed to do. Let's just do it anyway. Just because it might, well, it might tell us something. First of all, it's important to know that you're looking at difference of squares.
Yes, I realize that.
Okay. And now if I move, let's see, I want the sine. Actually, I think I did this wrong. It's sine of y squared minus sine squared of x. Notice that when I multiply this by this, I've got to do it in the right order.
Oh, that's weird.
In other words, I've got to have the sine y in front to make it difference of squares. And the first one was in the correct order. So now when I move this to the other side and this to the left side, I've got 1 equals 1. You see that?
Yeah.
Okay. So sometimes you can work backwards. In other words, that's probably not a satisfactory answer for your teacher. So how did I get this over here? Well, let me blow this up a little bit. I multiplied it by sine x, actually sine y plus sine x. And I multiplied the left side by cosine x plus cosine y. So, in other words, let's start, instead of cross-multiplying, which is one of the no-nos in proving trig identities, let's go ahead and multiply the left side by cosine x plus cosine y over cosine x cosine y. That is something you're allowed to do. Because all I'm doing is multiplying the left side by the number 1. Right?
All right.
Okay. What that gives me in the top is cosine squared of x minus cosine squared of y. Still the difference of squares. And in the bottom, I'm going to leave it undistributed, which is usually the best thing to do.
Okay.
Sometimes you want to distribute it, but a lot of times you don't. So at the moment, I will leave it undistributed. So as all I've done is messed with the left side. Now, has your teacher told you that you're not allowed to mess with the right side?
He said not unless you need to.
Okay, well, let's mess with the right side then.
All right.
And I'm going to do the same thing. I realized that what worked when I cross-multiplied was multiplying by sine x plus sine y. So I'm going to multiply the right side by this over itself. In other words, sine y minus sine x all over cosine x plus cosine y. I'm going to multiply it all by this, sine y plus sine x all over sine y plus sine x. And now the right side becomes sine squared y minus sine squared x all over a denominator that is exactly the same as the left side. So now all I have to do is prove that this numerator is the same as this numerator. And that's easy enough done. Using trig Pythagorean substitutions, cosine squared x is equal to 1 minus sine squared x minus cosine squared of y is 1 minus sine squared of y. Take away the parentheses, the 1's cancel. I end up with minus sine squared x plus sine squared y, which becomes sine squared y minus sine squared x, which is the same as that. Now, if it makes you feel any better to carry that denominator forward, we can do it. In other words, I can take this denominator, put it right there. Take this denominator, put it right there, and then all I have to do is make the numerators the same, and I've done that in this step here.
Yep.
Okay?
It's a lot of work.
Yes, it is. These are tough enough in one variable. When you go to two variables, they become even tougher. But this is actually a kind of a perfect example of where if it's really difficult to figure out, go ahead and do some things that you're not normally allowed to do because it kind of elucidates the problem and tells you what you need to do to the left side in order to make it look like the right side. And it's important that you understand the purpose of proving trig identities. There are no real-life problems that require you to prove trig identities. It serves one purpose and one purpose only. It teaches you your trig identities.
Yep.
If you do enough of them, you get really good with your trig identities. Your 11 primary trig identities that you have to use repeatedly. And that's really the only purpose of this exercise. Now, once you get into solving trig equations, it's a whole different story. There's all kinds of real-life problems that involve solving trig equations. But the secret of solving trig equations is to know your trig identities really well.
Yep.
So that's why they have proving trig identities before the chapter on proving or solving trig equations, because you just have to be really good, and this is a really good exercise for doing it. So in that regards, it doesn't really hurt to do things you're not supposed to, like cross-multiplying. That illuminated the problem enough for me that I was able to go back and do it properly using the proper method. The one strange method is this multiplying by the conjugate, which is, notice that that was my first step, was to multiply the conjugate of the numerator.
Yeah.
That is frequently something you have to do when you're proving trig identities, but it doesn't really have anything to do with knowing your trig identities. It's just a particular technique that is frequently useful. Usually when you see expressions like 1 minus cosine x, the answer lies in multiplying top and bottom by the conjugate of this, or 1 minus sine x, because those expressions can't be handled easily in any other way. If they're not squared, this thing is not equal to any other thing. So you end up doing that little trick of multiplying by the conjugate. All right, let's go to another one. Do you have to do just odds or every one?
Just 31, 33, and 35.
Okay, let's look at 33. Okay, I'm going to do this a different way. Biggest problem with online is figuring out how to fit my drawing tablet onto the screen.
Oh, yeah.
Okay. Well, you didn't start me out with easy ones, that's for sure.
No.
But that's the way it usually goes when you're a tutor. You don't get the easy ones.
Yeah.
Those, if I'm doing my job, you know how to do.
Yeah, I knew pretty well.
Okay. Even though I'm dying to square both sides, notice that if I square both sides, the thing is solved. Right?
That's a good thing.
In other words, if I square both sides, I got 1 plus sine theta in the numerator. Ooh, no, it's not quite solved. This ends up being squared, but then I've got 1 minus sine theta in the denominator over cosine squared of theta. Take the Yeah, let's think about this. Normally you work with the more complicated side. And to me, that would be the left side, yeah. Well, let's do what I talked about doing, which was whenever we see an expression like this, either the numerator or the denominator, it's worth multiplying by the conjugate. And the reason it is because when you multiply it by the conjugate, you turn it into 1 minus sine squared of theta, which reduces to cosine squared of theta. So since I'm looking at cosine of theta over here, the conjugate I'm going to use is the conjugate of the denominator. You know what I mean by that, right? The conjugate.
Yes, I do.
I'm allowed to multiply anything by 1 without changing its value. So that's what I'm doing. And in the top, I'm going to leave it like this because when I go to take the square root of it, I don't want it distributed. I want it just like this. The bottom becomes 1 minus 1 minus sine squared of theta, which becomes cosine squared of theta. Okay, well, I can separate this into numerator and denominator. So I got the numerator is going to be this. The denominator is going to be this. And what is that answer? Well, 1 plus sine theta in the numerator and plus or minus cosine theta in the denominator, which translates into the absolute value of cosine theta.
Absolute value.
When you get a plus or minus. And that's what they wanted us to show.
Cool.
All right. 35 next?
Yes.
Okay. This is actually a pretty easy one. If you use the cofunction identity, which is the cosine of pi over 2 minus x is always equal to the sine of x. Just like the sine of pi over 2 minus x is always equal to the cosine of x. These are the cofunction identities. This holds true between cosine and sine, tangent and cotangent, and secant and cosecant. Those are the cofunctions. So this whole expression can be turned into sine squared of x.
Yes.
Then you have cosine squared of x plus sine squared of x. We know that's equal to 1, so we have 1 equals 1.
Ooh, that actually was very hard.
Yeah, and in case you're wondering about that, well, this is actually cosine of pi over 2 minus x times cosine of pi over 2 minus x. So I can immediately change each of these into sine x.
And then get
Sine x and sine x is sine squared x.
Yeah.
Okay. 37. Right? It was all the odds. Am I correct, Max?
You can do 37 if you want. I didn't need it for the homework, but
let's do whatever you're the best director here.
I think I would rather go on to the 5.31.
Okay. Let's see, this was page 55. So let's close that page out. And that was that one there. the top one? This one here? I've got three other pages. Let me open this one. And let me open this one.
On one screen for me, it's not showing you doing anything.
It's not showing
there we
you?
go.
Oh,
That's moving.
wow. There's a delay there. I didn't realize there was that big of a delay. This is the third page. This is the second page.
All right, this is what we need to do next. This is, nope, not this one.
Probably this one.
Yeah, that's the bottom of it.
Let's see if I got the top. I got as
I
high.
found a different picture of the top.
It starts with 1. Maybe this is it. No, doesn't look like it. But we've got a half an hour and 3 pages to cover. So why don't you pick one? This is the first option, and that's all I can.
Let's do this one.
Let's do this one? Okay. Starting with exercise 5? Or start? Okay. This is a multiple choice? 2 choices only? Really?
I guess so.
Never seen anything quite like this. Okay, this is a free...
Verify that each x value is a solution of...
okay.
You just have to verify that those x values are solutions.
Verify by plugging them in?
I guess so.
Okay, let's do the more proper thing, which is to solve this equation.
Okay.
Okay? Because that's what they're leading to. In other words, they give you solving trig equations 101 here, and then this is solving trig equations 102. So let's just solve this equation and figure out whether these are the solutions or not. So what we're looking at here is awfully close to a quadratic. And in fact, it is proper to say that this is a quadratic in sine x. The equivalent quadratic polynomial would be this. Well, I'm allowed to make a substitution and say, okay, I'm going to let u equal sine x. And so what I'm really looking at here is 2u squared minus u minus 1. Now let's solve this. Well, it factors into 2u and u and minus 1 plus 1. Now we go back and resubstitute to get 2 sine x plus 1 times sine x minus 1.
Yeah.
So that's the way it's done, and after you get kind of used to it, you don't need to do this substitution step.
Yeah.
As long as you're good with going from this to this. Now let's solve this. If this statement is true, what needs to be true?
You have to equal 0, but I don't know how you would get there with the sign.
Well, if 2 things multiplied together equal 0, then one of them has to be 0.
Yes.
So either 2 sine x plus 1 is equal to 0, or sine x minus 1 is equal to 0. They both might be true, only one of them might be true, but at least one of them has to be true. Because you can't multiply 2 numbers and get 0 unless one of them is 0. Well, if we solve this one, we get sine x equals negative 1/2. What's x equal to if sine x equals negative 1/2?
I don't know.
What angle would sine of that angle equal plus 1/2?
Um,
Let me redraw these because these are critical, I think, for memorizing the first quadrant trig functions. Most all of the problems you're dealing with now are going to be one of these angles or a multiple of one of these angles. So if you memorize these two triangles with their dimensions, you'll be able to answer that question. So what angle is the sine of that angle equal to 1/2?
Um,
30 degrees, right? Opposite over hypotenuse. So the sine of 30 degrees is equal to 1/2. That means that x, if I said the sine of x equals 1/2, x would be 30 degrees. Well, we're saying negative 1/2. Sine is positive in the first quadrant and the second quadrant, and it's negative in the third quadrant and the fourth quadrant. So the third quadrant angle that's equal to 30 degrees is 180 plus 30. So that would be, their answers are in terms of pi, so let's make it in terms of pi. Instead of pi over 6, it's going to be 7 pi over 6.
Yeah,
That's
one of the answers.
That's certainly one of the solutions for sine x equal minus 1/2. There's also the fourth quadrant solution, which is 11 pi over 6. So I could actually say that also. And to solve the second part, sine x equal 1, where does that happen? And for that, we need the graph of sine x.
Which is, pi over 2.
So, and there's only one spot in the unit circle where that's true, and that is at pi over 2. So that's a solution, and both of these are solutions. So yes, both of these work. In other words, if we, the way it looks like they kind of want you to do this is by plugging pi over 2 in for x, proving that that is indeed an equation, and then plugging 7 pi over 6 in for x and proving that that's an equation also. So all I did was I skipped the substitution part of it and solved it directly based on it being a quadratic, which we're going to have to do in 7 through all the others.
Yeah.
Okay, so I'm confident that you know how to plug in x and prove that that's an equation.
Yeah, I can do that.
So let's go on. Although number 6 might be worth looking at, if we had to solve it from scratch, let's indeed take a look at it. It's not that hard to solve from scratch. It's also a quadratic. Notice that the only thing we need for something to be a quadratic is for this term to be twice that.
Yeah.
In other words, I could have a quadratic if I said as long as this thing is twice that thing, I've got a quadratic in secant to the third x. Well, what's my quadratic in up here? If I said this was a quadratic, you would say it's a quadratic in what?
Secant squared?
Yes, secant squared x. So when we factor it, it's going to be secant squared x there, secant squared x there. We want plus minus because of this negative sign. We're going to want 4 and 1. I want the larger factor to go with the sign of the middle term, so the 4 goes there, the 1 goes there. Okay. Now, if that's equal to 0, then secant squared x is equal to negative 1. Don't like that solution. That means secant x is the square root of negative 1. And cross that off right away. However, the second part of this says that secant squared x is equal to 4, meaning secant x is equal to plus or minus 2. With me?
Yep.
If secant x is equal to plus or minus 2, then cosine x is equal to plus or minus 1/2. Where is cosine x equal to plus 1/2?
At, I don't know, I'm struggling with this. 30 degrees.
Actually, sine of 30 is 1/2. That's something worth memorizing. So if sine of 30 is 1/2, cosine of 60 must be 1/2.
Is 1/2, yeah.
So x is equal to 60, which is pi over 3. That's one of the solutions. That's the first quadrant solution. We also have the fourth quadrant solution, 5 pi over 3. That's for the plus 1/2. The minus 1/2 cosine, that's 2 pi over 3 in the second quadrant and the fourth quadrant. So here are the 4 solutions for just this part of the problem. And those would be the 4 solutions to the entire problem. And notice that, yes, 2 pi over 3 works and 5 pi over 3 works.
Yeah.
All right. Let's go on to the, I assume, 7 you have to do?
Yeah.
Do you know how to do some of these? You want to start at 7 or?
7. You should probably just go for it. I don't want to do something wrong. I think that it's right.
Okay. What's the next step?
You could, would you move the 1 over?
Yeah, treat these just like algebra equations until you get to the final thing.
And then divide by 2.
And now solve. Now I notice they don't put a domain in here. Is it, well, once we get the answer, I'll ask you that question. So what is x? Where's the cosine of x equal to negative 1/2?
Negative 60?
Well, no, actually not, because the cosine of negative x is equal to the cosine of x. It's an even function. Let's look to our unit circle. In other words, whenever we're trying to go the other way here, I'm assuming they don't let you use calculators here.
Probably not.
Okay. So if we know all students take calculus, that tells me cosine is negative there and there, second and third quadrant.
Yeah.
So I need the angle such that this reflex angle is 60 degrees. Excuse me, the reference angle is 60. So what is this angle if the reference angle is 60?
120?
Right. 60 is pi over 3, 120 is 2 pi over 3.
Yeah.
I assume they want us to leave all of our answers in radians. So that's one place. The other place is where the third quadrant reference angle is 60 degrees. And what is that angle?
It's 340?
Right.
Or
It's
240?
240, which is 4 pi over 3. Now, to help with these formulas, the best thing to put on here is the formula for converting to that first quadrant. It's 180 minus theta, or pi minus theta if you're in radians. In the third quadrant, it's theta minus 180, the exact opposite, or theta minus pi. In other words, notice how once I knew that the first quadrant angle was pi over 3, pi minus 2 pi over 3 is equal to pi over 3. So in other words, I solved that equation. I go pi minus the angle I'm looking for is equal to that first quadrant angle, and theta becomes 2 pi over 3. So if you have these memorized from your unit circle, and this one is 2 pi minus theta in the fourth quadrant, in other words, you can always answer these questions if you have this diagram memorized.
Yeah.
So this would be the answers if they would have said in the domain 0 to 2 pi. But they didn't. So well, yes and no. I noticed that over here they do state that 0 to 2 pi, and they don't state it here. Let me just suggest what the answer is and see if you've ever seen anything like this. The first answer is 2 pi over 3 plus any multiple of 2 pi.
Yeah, we did that the first time.
It goes from 0, 1, 2, 3, dot, dot, dot. So that's the way to state an answer when the domain is not restricted.
Yeah.
And the other solution is x equal 4 pi over 3 plus k times 2 pi. K equals 0, 1, 2, 3, dot, dot, dot. This is the correct answer if the domain is not restricted.
Cool.
Just take whatever answers you get from that first quadrant or from that unit circle and add a k times 2 pi to them.
All right. Seems easy enough.
Unless it's tangent, and then it's a k times pi.
Yeah.
We'll get to that later. But the natural period of sine and cosine is 2 pi. The natural period of tangent is just pi. So when you're dealing with tangent, every pi is a multiple. All right. Which one next would you like to look at? This one solves pretty similar to this, only I get negative 1 over square root of 2, and I have to find what angle that is and go through the same process.
Yeah, these seem pretty easy.
Yeah, this one becomes secant of x equals 2 divided by root 3. You can find that angle. The key to finding all of those angles is by far memorizing these two triangles.
Yeah.
These two triangles right here will always answer any of these kind of questions. In other words, which angle is the sine equal to 1 over root 2? Well, 45 degrees. The sine would be 1 divided by root 2. So x is the first quadrant angle would be 45 degrees, but since it's negative, it's got to be in the third or the fourth quadrant. So you look for those angles that are the equivalent of 45 degrees in the first.
Yeah.
All right, so let's skip to 11.
Okay.
Because 11 is the first one that does something different. Although, I mean, as long as you know how to handle these three these equations like secant x. In other words, once I solve 9 and I get it to secant x equals 2 over root 3, the way I answer this is by saying that means cosine x is equal to root 3 over 2, and then I solve that.
Yeah.
Rather than trying to solve this. I find it far easier to work in your 3 primary trig functions and convert to the secondary or vice versa. If you get good at solving that when it's secant, more power to you. But it isn't necessary. You can always take its reciprocal.
Yeah.
All right, so let's deal with a tougher one, 11. So here we have cosecant squared of x equals 4/3, right?
Yeah.
What's the next line?
Cosecant. Would you take the square off?
Well,
I don't know. Would you just do square root
plus,
of 4 over 3?
plus or minus.
Oh, yeah, okay.
Plus or minus is very important because the plus is going to give you 2 solutions and the minus is going to give you 2 solutions. So there's actually going to be 4 solutions to this. And if I leave out that plus or minus, you're only going to find 2 quadrants where this is true. So you'll miss half of the solution. Now, I can reduce this a little bit to make it plus or minus 2 over root 3. And if I go back to my 3060, this is the 2, this is the root 3, this is the 1. So what angle is the cosine of x equal to 2 over root 3? Cosecant x, excuse me.
At 30.
Well, 30, the sine is 1 over 2, which would mean the cosecant would be 2 over 1.
Oh, I was thinking cosine. Yes, it's 60.
It's 60 because the sine of 60 is root 3 over 2, which means the cosecant of 60 is 2 over root 3. So 60 degrees is the angle that we're looking at, and we need that angle in all 4 quadrants. So we need to figure out what's the equivalent angle in all 4 quadrants. That's equal to pi over 3. Notice that the denominator times the degrees is always equal to 180.
Yeah.
Okay. So pi over 3 is one answer. That's plus 2 over root 3. Let's go through all 4 quadrants. If pi over 3 is one answer, this is pi minus theta. So in the second quadrant, what is the angle we're looking for?
Pi minus theta.
In other words, we would solve this equation. Pi minus theta has to equal pi over 3.
Yeah. So then theta would be 150 degrees?
Okay.
No,
that's
it's
correct. No, that's
pi over
correct.
3,
That's
so
2 pi over 3, but you can leave it all in radians. You don't need to go to degrees.
Oh, okay.
So if I move theta to the right, move the pi over 3 to the left, I'm left with 2 pi over 3.
Yes.
So that's the second quadrant answer.
Yeah.
The third quadrant answer is theta minus pi. So theta minus pi has to equal pi over 3. What's theta?
Theta minus, it would be 210 degrees, which is, I don't know how to put that into
Actually, it would
radians.
be 240. Let's solve this as an algebraic equation. We get theta equals pi plus pi over 3. Well, this is 3 pi over 3 plus pi over 3, so that would be 4 pi over 3.
Yeah.
In other words, it might just be easier to leave it in radians and don't go to degrees and use these instead of the degree equations. Remember, the fourth quadrant is 2 pi minus theta. Okay? So we've figured out the first, second, and third quadrant. What's the fourth quadrant? In other words, 2 pi minus theta has to equal pi over 3.
Yes. So then that would be 300 degrees. No, that wouldn't be it. It would be 330.
300 is right.
I don't know. 300 is right. Okay.
Yeah, because if I subtract 60 from 360, I get 300.
Okay.
I'm sorry. If I subtract 300 from 360, I get 60. But the easier way to do this, once again, is to solve this algebraically. Move the theta to the right, move the pi over 3 to the left, and then just solve that. 2 pi minus pi over 3. 2 pi is 6 pi over 3. That's 5 pi over 3.
5 pi over 3.
Uh-huh.
Cool.
So those are your 4 solutions for this problem. And we would kind of expect 4 solutions because, first of all, we're looking at a quadratic. So we know there's going to be 2 regular solutions. But then when we're dealing with trig, usually one solution gives you 2 answers, 2 quadrants where it's true. So we would expect 4 solutions to this merely because it's a quadratic. Okay, which one would you like to do next? Let's do 10. I see something in 10 that's a little interesting. Where is that true?
The inverse of tangent. I don't know. I don't know tangent very well.
Well, cotangent is the reciprocal of tangent.
Yeah.
So if the cotangent of x is equal to minus 1, and the tangent of x equals 1 over the cotangent of x, then the tangent of x has to be equal to minus 1 also.
Yes.
In other words, it's the reciprocal, and the reciprocal of minus 1 is minus 1. So now we're solving this. Where is the tangent equal to 1? Let's solve that first of all.
Could be at 45 degrees or pi over 4.
Okay, so that's the first quadrant angle. But it's a negative 1, so we know it has to be either in the second or the fourth.
Yes.
So if we go back to that unit circle, and we try to stay in radians, so it's pi minus theta in the second, theta minus pi in the third, 2 pi minus theta in the fourth. So the second one, what angle would theta have to be such that pi minus theta was equal to pi over 4? Pi theta equals pi over 4.
Then it would be 3 pi over 4.
Good. So that's one spot where tangent of that angle is equal to minus 1. Now the fourth quadrant. The fourth quadrant says 2 pi minus theta has to equal pi over 4.
Yeah.
Solve this algebraically.
Then you would get 7 pi over 4.
Those are your two solutions.
Cool.
Now, this only has two solutions because it's a linear equation. It's not squared. So we would expect one solution, and then of course one solution usually has two different quadrants where it's true. And that's the case there. All right, let's see. We don't have much time left. Is there
Not really.
a particular problem that you want to see done? I think you probably know how to do 11, 12, and 13. They're similar enough to 11.
What would you do on 16?
All right, I was going to suggest 15.
15 is probably better, though.
Let's talk about 15 because this is something you have to do a lot. When you have an equation that is in two different trig functions, generally you have to get it into the same trig function. 16 doesn't have that problem. Everything's in tan. I can just set that equal to 0 and solve, or I can set that equal to 0 and solve. So 16 is actually very straightforward. You're going to have you're going to have a plus or minus 3 there, which is going to give you lots of solutions. There's going to be 4 solutions for just that part, and then there's going to be 4 solutions for that part. So this actually is going to have 8 solutions. But let's go back to 15 because 15 illustrates two different trig functions in the same equation. So what can we do here?
You could move, well, would you make the sine into cosine first before you move it?
Yeah, it doesn't matter whether we do it before or after we move it, but we're either going to convert our sine squared into cosine squareds or our cosine squareds into sine squareds. And it doesn't much matter. Let's just convert this one real quick since that's easy. Now we have a quadratic in cosine. And in fact, if I solve this, I get 4 cosine squared of x equals 1. So cosine of x equals plus or minus the square root of 1 over 4.
Yeah.
Okay, which is equal to plus or minus 1 over 2. So we need all of the angles where cosine is equal to plus 1/2 and minus 1/2. And I think we did this exact problem. No, that was sine. Nonetheless, this should be relatively easy. What's the first quadrant angle? Where cosine is equal to 1/2.
Would that be 60?
Or pi over 3.
Or pi over 3.
What's the second quadrant angle? After a while, you start kind of recognizing a pattern.
It would be
Pi minus pi over 3.
that's what I was thinking. It would be 2 pi over 3.
The third quadrant angle would be pi plus pi over 3.
So 4 pi over 3.
And the fourth quadrant angle would be 2 pi minus pi over 3.
So then 5 pi over 3.
Notice the pattern
Yeah.
for cosine. And that's not always going to be a pattern. That's a pattern when it's pi over 3. If it's something other than pi over 3, you don't have that pattern. In other words, if it's pi over 4, second one is 3 pi over 4. The third quadrant is 5 pi over 4. And the fourth quadrant is 7 pi over 4. Notice the pattern's a little different. It's 1, 3, 5, 7 instead of 1, 2, 4, 5. So I'm not suggesting you memorize those patterns, but when you do enough of these, pretty soon the patterns start making themselves evident to you, and it makes it a little easier to handle.
Yeah.
Okay. So that's what you do when you have different trig functions, is try to get them all into the same trig function.
Okay.
Okay. For instance, 33 has a sine squared and a cosine. Well, if I convert this to cosine squared, which I can do, then I have a quadratic in cosine, right?
Yeah.
I have a quadratic in cosecant here. Here, I got to convert one of these to cotangent, or cotangent to one of these.
Easy.
I got to combine these somehow. 36 is a little tougher. 36 says use a graphing utility. Let me tell you really quickly how to solve 36. You let y sub 1 equal the left side of the equation. You let y sub 2 equal the right side of the equation. You graph it, and wherever they cross, that's x.
Yeah, we did one of these before.
Okay. All right. Between all those principles, you actually should be pretty set on solving trig equations also. So,
yeah, this really doesn't look too bad.
Yeah. All right, let's see. We have another appointment set up for tomorrow? No.
Do we?
No, we don't. Next Wednesday at 6:30.
Okay.
And that's in person also, correct? I mean, that's
what
online. You prefer to do that online, right?
Yeah.
I'm going to make that go from 6:30 to 7:30. When you schedule, when you or your parent schedules these, there's always two options. There's the online option and there's the in-person option. Make sure you choose the online option, which will only block out a 1-hour time period.
Okay.
The in-person option blocks out a 2-hour time period, which you don't really need.
Okay.
Okay? And I'm always happy to make the appointment myself also, if you don't want to do it online. But anyway, I will talk to you Wednesday.
Yeah. Wait, so that was at 6:30 to 7:30? Is that what that said?
Yeah. Yes.
Okay.
So I will I'll text you that meeting ID at 6:30.
All right. Cool.
Okay, Max. All right. Bye-bye.
Thanks.